Welcome again to the Shock and Vibration webinar series. My name is Tom Irvine and I'm the instructor for this series. And I would once again like to thank the NASA Engineering and Safety Center, NESC, and Dr. Curtis Larson for sponsoring this series of webinars. The topic for today is the general method, or we might call it the better than miles method, for calculating the vibration response spectrum. So this will be a new function for us. And it's based, again, on the single degree of freedom response. So here we have a spring mass system, and it's subjected to a base input, and that base acceleration is y double dot, and the absolute acceleration of the mass is x double dot. And then we have the mass. The Hooke's law gives us the stiffness k, and the damping coefficient c. And the natural frequency of this spring mass system is 1 over 2 pi times the square root of the stiffness k over the mass m. So in our previous unit, we considered the case where we had a Psd base input, and the natural frequency and q values were either known or assumed. And we were able to look at the response of single degree of freedom systems in the frequency domain. And we're going to do a little bit of review along those lines, and then we're going to introduce a new function, and it's going to be called the vibration response spectrum. And this is going to be a function whereby we allow that natural frequency to be an independent variable, which can vary between lower and upper frequency bounds. Now this equation should look familiar to you if you participated in the last webinar or viewed the slides. So sometimes I call this the general method, and sometimes I call it the better than miles method. So just take your pick as to which name you prefer. But the idea is to calculate the acceleration GRMS response to a power spectral density base input. That's going to be y caret, and the base input Psd can vary as a function of the excitation frequency. So it can have peaks and dips and valleys and ramps, plateaus, slopes, whatever you can imagine. It can be defined over a finite frequency domain. And again, on the left side, we have the overall response acceleration. This is the absolute acceleration. And it also, in addition to depending on the base input Psd, it also depends on the natural frequency of the system, and then in this case you have the viscous damping ratio, or you could think about it in terms of the equivalent Q value, where Q is the amplification factor. So embedded in this equation on the right hand side, this is the power transmissibility function, and we talked about that in the last webinar. And this rho term here, rho sub I, this you could think about it as a normalized frequency or a non-dimensional frequency, and that's equal to f sub I, where that's the excitation frequency, divided by the natural frequency f sub n. So we take this power transmissibility and we multiply it by the base input power spectral density, and we do that frequency by frequency. Now the base input Psd is going to be digital. So we've got digitized data, and there's going to be a frequency step between each of the spectral points in the Psd. So we have to multiply here by delta f sub I. Typically, delta f sub I would be, it could be constant, a constant step, but in some cases it could also be a step in terms of octave bands, maybe like a 1/12th or 1/48th octave, whatever. Either way, we can use this formula. And what this comes out to be is really the square root of the sum of the squares. It's that type of a calculation. And that gives us the overall response GRMS value. Now, it's one thing to look at this equation, but it's probably a little better if we start actually doing some examples so you can see some curves, response curves. Then this will start to make a whole lot more sense. And again, this is largely still a review of our previous webinar. Now here's one thing a bit new. This is going to be our power spectral density that we're going to use for the start of this webinar. It'll be a base input power spectral density. And we've been using the NavMat Navy level quite extensively, so I decided it was maybe time for a new base input PSD. So this one, it looks similar to the NavMat level, but some of these breakpoints are actually a little bit different. And it comes from Mil Standard 1540C. And likewise, it's in Mil Standard 1540B as well. And it's used for testing avionics components on shaker tables. So it's a power spectral density. The overall level is 6.14 GRMS. The y-axis is acceleration, g squared per hertz. Well, that's really GRMS squared per hertz, but we simplify it as g squared per hertz. Then along the x-axis, we have the frequency in hertz, and then the 4 coordinate points. And as usual, this is in log format. Now let's go ahead to our MATLAB here, and we're going to access the input files for this MATLAB webinar today a little bit different than we had in the past. In this case, I have all the files for this unit in a .mat file. So what I'm going to do is show you how you can load that up using our vibration data GUI package. So let's go to our MATLAB workspace, or command window I should say here. We'll type in vibration data and pause for a second. Okay, there it comes. Now vibration-data.m is up to version 5.2 and rising, so please check with the blog to get the latest version of the vibration data GUI package. And I suppose by the time you view this unit, an even higher version will be available. But let's go with 5.2 for now. So what we can do, and this is a newly added feature under import data. Import data has been there for previous versions, but let's go to this and see what is new. So now what we can do for our input data is we can, now typically we've been using this, well, we've always used it in the past to call in an ASCII text file. But now we're going to load a MAT file. So I just click on this load button here. And for today, we're going to be using webinar_16_data_files.mat. So just click open and then return. And then what I should see here is that, I encourage you to do this yourselves. In the MATLAB workspace, there are 4 arrays that have come up. And these are the 4 arrays that we're going to be starting with for this webinar. And the Mil Standard 1540C level that I talked about is in this file here, or I should say array, called M1540. So now what we're going to do is, I'll call up a WordPad here. Let's go ahead and this will be somewhat of a review exercise, but we're going to extend it to work up to our vibration data, or our vibration response spectrum, I should say. So let's go back to vibration data, and we're going to have a power spectral density. This will be our input data, power spectral density. And we're going to do the single degree of freedom response to the base input. So this is the general method, or you could call it the better than miles method. Let's click on this. So this script calculates the response of a single degree of freedom system to a base input power spectral density. The input array must have 2 columns, frequency in hertz, and acceleration in units squared per hertz. Well, for today our unit is going to be our G unit. So we're going to use these English units. Now we've got an array preloaded in MATLAB. This is the Psd array, and it's called M1540. So that's our base input power spectral density from the Mil Standard. Interpolate, yes, it's a specification. Let's start off with 100 hertz natural frequency. Q is equal to 10. And I'm going to do the plot from 20 to 2000 hertz because that's the frequency limits for that Mil Standard 1540 level. Duration. Now, duration is not going to be important here because that only affects the maximum expected peak, and we're just going to be focusing on the GRMS level. But let's just go ahead and just say 60 seconds. calculate. Okay, a couple of things, a couple of different plots come up here. We also have some data appearing in this results box here. So for 100 Hertz, I'm going to round that off to say 6.4 GRMS. That's our response. A couple other parameters, pseudo-velocity, relative displacement. But let's go here to this plot. So these curves are both power spectral densities. The green curve is that base input from the mil standard 1540 level. The blue curve is the response of a single degree of freedom system with a natural frequency of 100 Hertz and a Q value of 10. So we've got acceleration g squared per Hertz versus frequency in Hertz. Both axes are log format. As far as the lower input energy is concerned, the system has unity gain. That is, as the energy frequency, or the input frequency approaches the natural frequency of the spring mass system, then the absolute acceleration response has some resonant amplification going on. So this is where we get our resonant amplification. It's at 100 Hertz and the frequency band thereabout. At higher frequencies, the spring mass system is filtering out the energy. So what we've done is we've taken that equation I showed you a couple slides ago, and we've applied it to this base input, and that has given us the response. Well, actually, I should say the transmissibility function embedded in that equation gives us the response Psd. Then as we take the area under the curve, take the square root of the area of the curve. Now that's equivalent to taking the square root of the sum of the squares. That gives us our response of 6.4 GRMS if I round off to 1 decimal place. So that's what's going on at 100 Hertz. Now, do we always know what the natural frequency of our component is? Ideally, yes. In practice, no. If we have, for example, an avionics box, hopefully we've had the chance to take the cover off the box and maybe mount an accelerometer on the circuit board and maybe put the avionics box on a shaker table and find out what the natural frequency is using some kind of a sine sweep test, for example. Well, even then we have to agonize a little bit because we might say, oh, but that accelerometer has a mass loading effect on that circuit board, so that kind of skews the data or affects the data. Well, if we can use a laser vibrometer, we can get a better measurement because there is no mass loading effect. But we need line of sight to do that, and also more money in terms of instrumentation. But the fact is, in many cases, we don't even have the chance to do this type of a test. If we're working with maybe a one-of-a-kind avionics box, or there's just 2 or 3 of them for 2 or 3 different flights of the same vehicle, the program managers might not want to spend the money to give us a spare unit to do the type of mechanical engineering tests we would like to do. So a lot of times we just sort of get stuck, and we have to just make estimates as to what the lower and upper frequency bounds of that circuit board inside that box would be. So anyways, let's go back to our data here. Here's the power transmissibility function. It relates the g squared out divided by the g squared in as a function of frequency. And you can clearly see we get a spectral peak at 100 Hertz. That's the natural frequency. And this spectral peak is 100. Well, 100 is q squared. So we could say the power transmissibility at the resonant frequency is equal to q squared. Or you could say that q is equal to the square root of the peak power transmissibility. But you got to be careful with that rule, because that really only works for single degree of freedom spring mass systems. If we have a cantilever beam or a plate model or finite element model, or we have a multi-degree of freedom system with several springs and masses, well, that neat and tidy rule no longer works. That's why when we like to use a half power bandwidth method as an alternative method for determining what the Q value is for the case as if we had measured data. Well, In this case, we already know what the Q value is because this is all an analysis, but imagine that this were measured data. Then we should use the half-power bandwidth method. Okay, but let's go back here and say, what if instead our natural frequency is 200 hertz? So maybe we're doing calculations for a family of natural frequencies, or we're trying to do a parametric study, or we're just trying to get an idea what the overall GRMS response is within lower and upper frequency bounds for natural frequency. So everything the same except natural frequency. Calculate. So here's the pair of power spectral density curves for 200 hertz. Now in this case here, the overall response is 11.1 GRMS. So that response is going up. And you can clearly see that we have unity gain at the lower frequencies. Then we get resonant amplification effects as we approach 200 hertz. And then this crossover frequency should be 200 hertz times the square root of 2. And above that point, attenuation or filtering is occurring. So that is, again, the response PSD and the base input PSD, where the response is for 200 hertz, Q is equal to 10. Well, what if and then the corresponding power transmissibility. What if we were even less sure about what the natural frequency was for our components? So we decided let's check 300 hertz in case it's higher. So for 300 hertz, so I'm making notes of these numbers because they're going to become important here shortly. We've got 300 hertz, and we have a response of 13.7 GRMS. So the square root of the area under our blue response curve is 13.7 GRMS, and that's for the case of 300 hertz. Q is equal to 10. And by the way, Q is equal to 10 is equivalent to 5% damping for a fraction of critical damping. So that's the pair of input and response curves at 300 hertz. And then we have the power transmissibility at 300 hertz. Okay, so let's just think about what we've done so far. So we have actually come up with it. We could make a little table here and say natural frequency in hertz. And I probably should have done this in an Excel spreadsheet so it would look a lot cleaner. And our second column here is acceleration GRMS. So what if we were to make a plot of the GRMS value versus natural frequency in hertz? What would that plot be? Well, that plot is going to be something called a vibration response spectrum. But before we do that, I just remembered I wanted to do one other thing. And we're actually going to have to backtrack a little bit because I kind of got my mind got preoccupied with a few other points. Let's go back and recalculate 100 hertz natural frequency. And let's save this as RSEP 100. So that's the response at 100 hertz. Let me go back and calculate 200 hertz natural frequency. Calculate. And I'm going to save this as RESP 200. Then let's go 300 hertz and calculate. And that's RESP 300. So I've got the three response PSD curves in the MATLAB workspace. So you can see over here on the right we have the files listed that are in the workspace for today so far. So let's go to plot utilities, begin signal analysis, and we're actually going to do multiple curves here. So our first curve is going to be M1540, and that's our base input PSD. So I'm just going to say input I call it a 6.14 GRMS. Let's just round it off to 6.1. Then we have the response at 100 Hertz. So I'm going to call this RSP, excuse me, I'm going to call this FN for its natural frequency, 100 Hertz. And this had a response level of 6.4 GRMS. Then RESP 200, it's going to have a natural frequency of 200 Hertz, and this was 11.1 GRMS. Then we have RESP 300, and that has a natural frequency of 300 Hertz and 13.7 GRMS. Okay, tidal, and we're still doing power spectral densities, but we're getting really close to doing a vibration response spectrum. We're really close. Let me call it figure 6 just to make sure I don't interfere with any figures that may already be existing. The x-axis label is frequency in hertz. The y-axis label is going to be Excel, g² per hertz. Let's make both of those log axes. Domain limits for x-axis, we're going to go 20 to 2000 hertz. We're going to plot all 4 curves, so we click on each of these radio buttons. And let's plot and see what we have. And I'm going to do something else too. I'm going to check this y-axis here. And let's make that upper level of 10 and lower level about maybe 1 times e to the 3. So I go over to here. Our maximum is 10. Our minimum is 1 e to the minus 3. Replot the curves. Okay, there we go. So this is a family of 4 curves. The blue curve is our base input Psd. And of course, this is a power spectral density function, acceleration g² per hertz versus frequency in hertz. Again, the blue curve is our base input, 6.1 GRMS. The response at 100 hertz is the red curve. The response at 200 hertz is the black curve. The response at 300 hertz is the green curve. And the overall GRMS levels for each of those 3 curves, actually for each of the 4 curves, is carefully noted there in the legend. So this is the type of thing that we would need to consider, for example, if our avionics box or electronic component needed to withstand this Psd, and we're trying to understand maybe for design purposes or before the test occurs, what does our box need? What will it be exposed to? What will be its response to the exposure? Well, we know what it'll be. We know what the exposure input will be. It's this base input. But the question is, what will its response be? Now, I should also note that we're assuming single degree of freedom response with Q is equal to 10. So we're assuming we know what the damping is. It's equivalent to 5% damping, which gives us a Q of equal to 10. But we're saying we don't know what the natural frequency is. It could be as low as 100 hertz. It could be as high as 300 hertz, for example. So this just gives us an idea of what our absolute acceleration response of our component or maybe our circuit board will be given that set of assumptions. This could also aid us for design purposes. Maybe we're designing the mounting stiffness for our component. If we have a relatively stiff mounting, we might get 300 hertz as the natural frequency for the component with 13.7. But if we have a more compliant mounting, we could reduce the overall response by about a factor of actually a little bit greater than 6 dB if we go to 100 hertz, because that would only be 6.4 GRMS response. So those are just some things to start thinking about. But the next step we want to do is what I started to tell you earlier before I forgot that I wanted to plot the family of curves, is that we've got these 3 data points and we want to plot them into a new type of curve that's going to be called a vibration response spectrum. So let's go ahead and I'm going to click out of this and click out of that. So if we go to power spectral density, we go to vibration response spectrum, and let's begin our signal analysis here. This script calculates the vibration response spectrum, or VRS, of a single degree of freedom system subjected to a base input power spectral density. The input array must have two columns, frequency in hertz, and acceleration, and in our case we're going to have g squared per hertz. So our input array is preloaded, and it's M1540. That's the mil standard level. English units. We're really going to be concerned just with the GRMS value. Let's just go ahead and throw in a duration of 60 seconds here. That really only affects the peak, maximum expected peak from the Rayleigh distribution. It will not affect the GRMS value, and it will not affect the 3 sigma value. Q is equal to 10. Now, if we were doing this in earnest, we might want to consider several different Q values too, and do a little parametric study. Just keep that in mind. Today's webinar is a bit simplified. We're only looking at one Q case, and that's Q is equal to 10. The plotting frequencies will be from 20 to 2000 hertz. And let's go ahead and calculate and see what we get here. Okay, first we see the relative displacement curves. Let's kind of park those off to the side. And on the right we have the acceleration curves. Now, each of these plots is a function of natural frequency, and that's very important. This is not frequency in hertz. Rather, this is natural frequency in hertz. That's a very important distinction. And our peak value here for relative displacement and our peak value for absolute acceleration response, those are the two curves that depend on duration from the Rayleigh distribution. But the 1 sigma, now when I say 1 sigma, we're assuming a mean value of 0. And since the mean value is 0, then we can say that the 1 sigma value is equivalent to the RMS value. So if we knew ahead of time that our component needed to be designed and tested to this level, we could use this set of curves here to help us maybe design the mounting stiffness or the mass properties or so on. And it looks like from this red curve, which is the acceleration GRMS response, as long as we're below 600 hertz, the lower the natural frequency, the lower the acceleration response. So in that sense, it would be very good to have a very low natural frequency. So we might want to take that avionics box and mount it via isolator grommets or bushings or soft springs. But we have to remember there's always a trade-off. So as the natural frequency goes down, the relative displacement goes up. So if we're going to use isolator mounts, we need to make sure our isolators can withstand that relative displacement without bottoming out. There are likewise concerns about sway space, clearance, mechanical interference, loss of alignment, which may be concerns for some components, although not others. So just keep that in mind. We've talked about this before. There is a trade-off between trying to optimize our design or minimize it for absolute acceleration. There's a trade-off in regards to relative displacement. Okay, another thing I want to show you here is with this red curve here. Do you remember our 3 points here? So let's see if our 3 points fall along that red curve. So we go Tools, and I'm going to do a data cursor, and we go to 100 hertz natural frequency. So at 100, and we're not going to get exact, we're just going to get pretty close here. 100 hertz is about 6.4 GRMS along this red curve. Well, that's the same as this point here, the first row of coordinates in this little table. That matches up. Okay, let's do another data point, and I'm going to do selection style. I'm going to do mouse position. I'm going to do create new data tip. 200 hertz. Okay, at approximately 200 hertz here. See how close I can get. Well, okay, let's just leave it this. 200 hertz, we get 11.1 GRMS. Well, that matches up with this table over here. Let's do one more case. Let's do 300. So create new data tip. Okay, so at 300 hertz, we get 13.7 GRMS. That matches over here. So we've got 3 points that we found out using our better than miles equation method. We could come up with these 3 points. What we've done with the vibration response spectrum is let the software do all the bookkeeping for us. So what the software actually did is it started at 20 hertz and then went at some intervals along the way to generate the complete curve for a whole set of natural frequencies. So if we know what the natural frequency is, then we can just go back to using the better than miles method directly. But if we're unsure what the natural frequency is, maybe we established it's between upper and lower bounds, then we need to generate this type of vibration response spectrum curve. And actually we're going to find out there's several other very important uses for this vibration response spectrum as well. It's a very powerful tool, and I'm going to show you by example what it can do. Just as a review, the green curve here is the 3 sigma curve. Sometimes people will assume, engineers will assume that 3 sigma is the worst case, but I'm going to argue that this blue curve here is the worst case, assuming a duration of 60 seconds, because the blue curve takes into account the Rayleigh distribution. And the Rayleigh distribution can show us, depending on our natural frequency and our duration, in most cases, in most practical cases, the Rayleigh distribution will show that our maximum expected peak is above 3 sigma. And the higher the natural frequency is, the greater that sigma level will be in terms of respective ratios. So just sort of keep that in mind. That's one of my main points about random vibration, is your peak may be greater than 3 sigma. Typically it will be. Okay, so let's see what else we can do here. We actually have several other neat tricks we can do with vibration response spectrum, but I want to go back to the slides. Now, these slides here are just sort of a backdrop. So the things that I'm actually demonstrating to you are the plots are already copied and pasted in this PowerPoint slide set, but I wanted to show you how to actually do the MATLAB exercises, because I want you, as your homework, to go and just repeat everything that I'm doing. So this was our base input from Mil Standard 1540C. Then we took a look at our 3 cases at 100 hertz, 200 hertz, 300 hertz natural frequencies. And you can see each of the responses there. These are all power spectral density curves. So the blue curve again is the base input. And in the title here, I was a little more careful with my title than I just demonstrated. I said this is PSD, where we have a base input and single degree of freedom response with Q is equal to 10. So we were saying, well, in this case, we weren't quite sure what the natural frequency is. Maybe it was 100 hertz, maybe it was 200 hertz, maybe it was 300 hertz. So we generated this family of curves. And then we took the square root of the area under each curve, and we noted the GRMS value here in the legend. And then what we can do is take those 3 GRMS values and plot them as a function of natural frequency. And by the way, on these slides here, I have the instructions on how to access the functions for carrying out all of these exercises. So here was our table that we came up with, our 3 natural frequencies, our 3 corresponding response acceleration GRMS levels, and I've noted that this is going to be a vibration response spectrum with Q is equal to 10. And then this is the plot that I've essentially demonstrated to you already. This is the acceleration response spectrum. I've carefully noted that Q is equal to 10. That's the amplification factor. Along this axis, we have acceleration in G. This x-axis is natural frequency in hertz. And I've said this before, but this is not frequency in hertz. This is natural frequency in hertz. There's a very important difference. And then the 3 points from the table for the 100 hertz, 200 hertz, 300 hertz, are plotted along this 1 sigma curve, which is also the RMS curve, assuming a zero mean. So please go ahead and repeat that exercise yourself so you can get a feel for, so you can practice really. Now we're going to move along to another example here. And this is a very interesting one because this is actual case history. There's nothing imagined about this plot. It really happened way back in the early 1990s, actually. In this case, we've got a pair of power spectral density curves. So we have g² per hertz versus frequency in hertz. The blue curve is actual flight accelerometer data. So measured flight accelerometer data from a launch vehicle. And we're going to assume that this was an accelerometer mounted near an avionics component. So in other words, the blue curve was the base input to the avionics component in terms of power spectral density. Then the red curve here is the test specification. So the component was tested to the red curve prior to flight. So now we're in the post-flight data review meeting, and we find out that the blue curve from the flight data exceeded the test data, the test spec, I should say, at 3 frequencies. So there's an exceedance at 330 hertz, there's an exceedance at 472 hertz, and there's a minor exceedance at about 810 hertz maybe. And by the way, I'd like you to work with these curves yourself, and the MATLAB arrays are flight underscore data for the blue curve and test underscore spec for the red curve. So you can actually go to vibration data, miscellaneous functions, plot utilities, and you can use the multiple curves utility to superimpose these two power spectral densities. So the question is, was this component under-tested? Well, if we knew what the natural frequency of that component was, that would help us answer that question. Now, if our natural frequency of our component was 330 hertz, then it would seem that our component was under-tested. Or if our component natural frequency was 872 hertz, it would seem that our component was under-tested. So let's assume that now this was an unmanned suborbital flight, but the avionics were not recovered. But there's going to be a series of these launch vehicles and a series of the same model numbers but different serial numbers of the avionics box. So next time around, do we need to modify the test level so we can envelop the flight data peaks on the flight from flight 1 so that we can, for test 2 or for flight 2 or flight 3, we can have higher test levels so we can cover these spectral peaks? Do we need to do that? Well, one of the problems is for mechanical engineering purposes, this avionics box is a black box. Due to costs and schedules and hardware availability, as mechanical engineers, we did not, nor will we have the opportunity to determine what the natural frequency is of the component, particularly of its circuit board or boards. But what can we do? Now, as we look at these curves, we see that the blue curve here, its overall level is 2.9 GRMS. Well, the test level is 7.8 GRMS. So that is maybe 7 or 7.5 dB higher. So in terms of overall level, this test curve here with its broadband energy has a much higher overall input level relative to the flight data. But on the other hand, the flight data has these kind of narrow band peaks here that exceed the test spec in terms of g² per hertz values. So what can we do? Can we somehow take advantage of the fact that this red curve is much broader and it has more overall energy to show that even if our component did have a 330 hertz natural frequency, that it was still tested sufficiently? Can we do that? And the answer is we've got a wonderful tool called the vibration response spectrum that will allow us to make that comparison. So let's go ahead, let's go back to vibration data. Vibration response spectrum, so power spectral density. And then we go to vibration response spectrum. It's there in the middle. So our input now, we're done with mil standard 1540. Our input level is going to be, let's start with the test underscore spec. We're going to assume Q is equal to 10. We're also assuming single degree of freedom response. Q is equal to 10. We're only going to do a GRMS comparison, so duration doesn't matter. Let's just leave it at 60 seconds. And let's go ahead and calculate what our response would be, vibration response spectrum would be for the test underscore spec base input. So a couple of curves pop by. Here's our test spec PSD. We've seen this before in a PowerPoint slide. Base input there. Relative displacements, let's ignore. And here's the acceleration RMS, the GRMS values essentially for the 1 sigma curve anyways, plotted as a function of natural frequency. Now it looks like I need to go back into that software and fix it so it'll display 3 decades because our curve got cut off, but the data is actually present there. So the red curve is what is of interest for us. So let's go and let's save this. Let's save that 1 sigma curve. We're going to save the 1 sigma curve, which is the GRMS curve, assuming 0 mean. And I'll just call this test spec underscore VRS. So this will be saved for the internal MATLAB workspace purposes. Okay. Now the next thing we're going to do is the same calculation for flight data. So our flight data is already in a PSD format. It's already in frequency in hertz versus g squared per hertz. Everything else the same. We'll give it a different name. We'll call this the flight underscore data VRS. So first we're going to calculate, then we're going to save. So here's the flight data power spectral density. We've already seen this before. Due to limited telemetry bandwidth, it's cut off at 1,000 hertz, but at least we got some data. Relative displacement, again, I need to fix the decades there, but we're not going to pay too much attention to that one. Now here's the acceleration vibration response spectrum for our flight data. So we've got G here, and for the case of the red curve, that's GRMS, or 1 sigma G, versus natural frequency in hertz. So now that we have this data, let's go ahead and save it in our MATLAB workspace. So the next thing we're going to do is we're going to do a comparison of 2 1 sigma VRS curves, or vibration response spectrum curves. Go to Plot Utilities. Let's go to Multiple Curves. We could also use the 2 curves option, but the multiple, let's go ahead and use multiple curves. Okay, we're going to plot 2 vibration response spectra curves on the same plot. So we've got test spec underscore VRS. Then we have flight data VRS. So we've got test spec, flight data. Let's see. We're going to call this the VRS, so this will be Q is equal to 10. And make it figure 9. Sometimes if we have pre-existing figures, we get figures written on top of other figures. So if I make it figure 9, that's a safe choice. Natural frequency in hertz. It's very important. I keep saying this over and over again. It's natural frequency in hertz. Log, manual. We'll plot from 20 to 2,000 hertz here. Y-axis will be acceleration, and let's go ahead and put RMS for the GRMS there. Log, plot curves 1 and 2 together. Okay, now here's our comparison. These are both vibration response spectrum curves. I've noted Q is equal to 10. Y-axis acceleration GRMS. X-axis natural frequency in hertz. The blue curve is from our test spec. It's the smoother curve of the 2 curves. The red curve is of our flight data. So what this is telling us is that for a single degree of freedom system assumption, and Q is equal to 10, that even at 330 hertz, our system will have a greater response level to the test spec than it would to the flight data. And the same thing is true at 870 hertz and 810 hertz. So, and there's margin to spare. So across all natural frequencies, the test spec provokes a higher response for a single degree of freedom system than does the flight data. And that comes about because this test spec is a broader spectrum and it has more overall energy in terms of the base input PSD than does that flight data. So what this is saying is that our component was not under-tested. There is margin to spare, and there is no compelling reason to change our test level for the next time this component is to fly. On the same launch vehicle with a similar trajectory, all other things being equal. And I want to talk a little bit more. I need to be a little more clear and honest and upfront with this as well. So let's go to our comparison here with our PowerPoint slides. So we go to PowerPoint slides here, and this just gives you the verbal description on how to go through and to do that exercise, calculating the VRS for each of those two data arrays. They're both power spectral density base inputs. Now, we've seen this plot before. In this case, it's only 2 decades, but this is what I just demonstrated to you. This is the plot that we can generate in our vibration data GUI package. So the red curve in this case is the test spec. The blue curve is the flight data. You've seen this plot before. X-axis, again, is natural frequency in hertz, with the y-axis being acceleration, response acceleration, GRMS. And the test spec has margin to spare relative to the flight data. Now, let's review our assumptions, because we need to be honest about our assumptions. We're assuming that our component is a single degree of freedom system. We're assuming it has Q value equals to 10. Now, we're allowing natural frequency to be an independent variable, and we have a wide range of natural frequencies. So as long as our component is from 20 hertz to 2000 hertz, we're good. We're also assuming that both the test spec PSDs and the flight data PSDs are stationary with normal distribution. That is a very safe assumption for the for the test spec, because the test spec we do on a shaker table, and typically the shaker table time histories for PSD tests are stationary, and typically they have a normal distribution. For the flight data, however, that is a more tricky assumption. Flight data tends to be non-stationary. It can have a non-normal or non-Gaussian distribution. And later on, we're going to be learning a method called rainflow fatigue and fatigue damage spectrum. And those will be more sophisticated methods that we can use. For example, if the flight data is non-stationary or if it has a non-Gaussian distribution. But today we're just kind of as a first approach here, a first step, to just learning the simplified vibration response spectrum method. We're also assuming that our test duration for our base input PSD on the shaker table is greater than or equal to the flight duration, or the duration during the flight at which the vibration was predominant here. And there's ways of looking at flight data to come up with a number of what the effective duration is. You can imagine a multi-stage launch vehicle undergoing, for example, some coast periods, and during the coast periods, the vibration levels would be negligibly low, and most of the vibration actually happens during liftoff and the first stage burn. Although in this case, I will give you some background that this launch vehicle also had a re-entry event where the vibration level was significant. But anyways, we are tentatively making these types of assumptions here. So let's when we say, yeah, the test spec envelops the flight data in terms of VRS, let's be clear about these assumptions.
Okay, now actually what a more common case history would be is that that could happen is that maybe the two curves would crisscross each other at several points. Maybe the flight data would be more of a zigzag curve. Well, in that case, as long as the red curve is higher than the blue curve over our estimated bounds of whatever our estimated bounds for the natural frequency are, then we can say we're good. Now, in this case, it's pretty easy because the red curve envelops the blue curve across all natural frequencies. And this whole methodology, in this case, we're comparing a test spec to flight data. That's one use of this tool. But imagine, for example, we had two different test spec levels. Well, how could that be? Well, let's say early on in the program, we have one test spec. It's a base input Psd. We test the component. It passes that Psd level. Then later on, as the program matures, there's new mission requirements. Now all of a sudden, we have a new test spec Psd. So the question is, do we have to retest the component for the new spec, given that it's already passed the previous test with a different Psd? Well, in order to resolve that question, we can turn to the vibration response spectrum tool. And hopefully we can show that our original test spec envelops our new test specs in terms of their corresponding response spectra. In that case, retesting is not necessary. Now, program managers never ever want to retest a component because that costs money, it costs time, it costs schedule slip potentially. And in the case of an actual flight unit box, we would start to worry about accumulated fatigue cycles if we're putting it through an additional round of base input Psd testing. So that's one of the things we get called upon as engineers, is to show, qualification by similarity or qualification by analysis, whatever you want to call it, or otherwise just to prove that retesting is not necessary. And to make our case really valid, it's best to know what the Q value is and the natural frequency is. But in some cases where we can only estimate within bounds, so we might have to consider a domain of natural frequencies. And we might also have to repeat the calculation for additional Q values as well. Now, in today's webinar, we're strictly doing Q is equal to 10. But out there, when you're doing your real-world problems, you probably want to do this for several other Q values. And we'll talk about what might be appropriate maybe later on. Well, you might want to say Q is equal to 10, and then maybe Q is equal to 30, for example. Those would be two good values to use, maybe. Okay, so now we've got another task yet. So we're going to find out that we can use our vibration response spectrum tool for something new, and this is going to be another powerful use of this method. So this is a different flight accelerometer Psd, and it's from a bulkhead on a launch vehicle, suborbital launch vehicle. So it's sub_bulkhead, and that's already preloaded in the MATLAB. We loaded that MATLAB at the start of the webinar. So power spectral density overall level 5.93 GRMS. We've got G squared per hertz along the y-axis. The x-axis is frequency in hertz. So at the bottom here, our task is given. We want to derive a simplified envelope using 4 coordinates. And this is going to be coordinates on log-log format. So imagine 4 coordinates with 3 connecting straight lines in log-log format. And we're going to say that we've measured this data, and now this is going to be a design and test specification for maybe a new avionics component. Well, actually, our task is going to be a little more complicated than that, because we have to also consider uncertainty margins and statistical safety factors and all that. And those will actually be covered in a future webinar. But for now, let's just derive the envelope, which will be the basis for down the road deriving an actual test and design level. So how would we envelope this data with just 4 coordinates? So some people might come along and say, well, let's be conservative, and it's really important that we envelop those peaks here. So this is a Psd plot, And we have our flight data. It's still overall level 5.93 GRMS. Now, this curve with the dark red lines here, we'll call that our candidate envelope. Its overall level is 10.3 GRMS. So you can see this red curve encompasses much greater energy than does the flight data. So if we take this, now you have to sort of look at the big picture too, because even once we've derived this envelope here, our job is not done, because then someone's going to tell us, oh, we have to raise that by 3 dB or 4.5 dB or 6 dB for a statistical uncertainty margin, because this was only one flight. And the next time this vehicle's fly, it might have higher levels. Well, that is true. It might have flyer. but let's add our conservatism on down the road and try and not be overly conservative at this step. So what we're leading up to, is there a way we can justify clipping these peaks as we derive our simplified envelope? Can we clip those peaks? And the answer is yes, we can justify clipping those peaks. Well, how can we do that? Well, how about we come up with various, let's use random number generation to randomly generate 4 coordinate points for maybe 1,000 or so different PSD base inputs. And then we're going to do some VRS type comparisons and some scaling. And let's scale each candidate PSD so that its vibration response spectrum envelops the vibration response spectrum of the flight data. So now all of a sudden, after that process, we've got 1,000 candidate PSDs. Then at that point, let's select the candidate PSD that gives us the lowest overall GRMS level. So that's what we're going to do. That may sound like a lot of work, but we have a MATLAB script that can do the bookkeeping for us. So let's see. This is going to be a trial and error process, and there's actually a few things built into it, like some scaling and convergence that maybe we can talk about at some other webinar unit. Let's just go ahead and see how this runs, though. We're back to vibration data. We go to power spectral density, envelop PSD via VRS, okay, begin signal analysis. So this script calculates a simplified, optimized PSD to envelop a base input PSD. The script assumes a single degree of freedom response with Q is equal to 10. The input array must be a base input power spectral density with 2 columns, frequency in hertz, and acceleration in g squared per hertz. So for our case, we have sub_bulkhead. And we're going to do 1,000 trials from 20 to 2,000 hertz. And this will actually give us 4 coordinate points. It's kind of hardwired into the software. But we can select either ramp, plateau, ramp, or we could select freeform. Let's just stick with ramp, plateau, ramp, and see what we get. So I'm going to hit the calculate button. And in the sort of at the bottom of the screen, you should be able to see that our progress in terms of how many trials that we've been through. So I'm going to get a drink of water while you watch that just for a minute, and I'll get back with you. There's actually 3 parameters. If you blink your eyes just right, you can see that the DRMS is the overall displacement, and the VRMS is the overall velocity, and the GRMS is the overall acceleration level. And those are for each candidate base input. Okay, so
we've got two graphs here, two plots. The one on the left here is the winning candidate. They're both power spectral density curves. The winning candidate is actually the green curve there. And that has an overall level of 8.21 GRMS. And you can see its corresponding breakpoints here in the MATLAB command window. And the blue curve here is our flight data of 5.93 GRMS flight data. What we've shown is that we can clip these peaks from the flight data. Now, throughout the industry, there's different kind of rules of thumbs. You might see that it's permissible to clip a peak by 3 dB, for example. And rather than just rely on those rules of thumb, why don't we use a VRS to guide us through that clipping process? And on the right-hand side, you see the corresponding vibration response spectra curves for each of the two base input PSDs. So the right-hand plot is vibration response spectrum. Noted as Q is equal to 10. We've got acceleration GRMS along the y-axis, natural frequency along the x-axis. And we find that this green curve, our envelope curve, envelops the flight data, which is the input data, across all natural frequencies. So rather than trying to envelop all of the peaks, we're saying that if we take 4 coordinates with 3 straight line segments, we can come up with this envelope, and it's 8.21 GRMS, and this is a more reasonable approach for enveloping this data, this flight data. Now, some of you should be thinking, well, yes, but what about flight-to-flight variation? What about spatial variation? What about, statistical uncertainty and all that? And my answer is yes, all those things are important. And if you need to increase this envelope by 3 dB or 4.5 dB or 6 dB, you're welcome to do so, and you should do so. But my point is, before we start adding all that margin, let's use the least possible envelope that we can, and our conservatism can come later on. So by the time we add our 3.5 or 4.5 or 6 dB, whatever it is, we'll probably end up enveloping all the base input PSDs anyways, but that's okay. I just wanted to show you what we can do as an intermediate step. Now, we need to be very circumspect about all of our assumptions we made there. So let's see. Let's see what we've got here. So here's an example where I did this already and put it into the PowerPoint slides. So the two pair of power spectral density curves there. So again, our enveloping method allows for peak clipping, and we're not relying upon any rules of thumb because we have our VRS justification. But with our VRS justification, we made some assumptions. Let's review these. We assumed single degree of freedom response. We assumed the amplification factor is Q is equal to 10. And effectively, we've assumed that both PSDs are stationary with a normal distribution. We're also assuming that in terms of our enveloping purposes, the duration that we assign to our envelope will be greater than or equal to our input duration, where the input's from the flight data. So again, we've shown that the envelope is greater than or equal to the flight data input across all natural frequencies. So this is a powerful tool for enveloping. But later on, we're going to be concerned about things like, well, what if that flight data had non-stationary time history? What if its histogram was non-Gaussian? What if the test duration and flight durations are some different numbers there? So what we're going to do in the future is we're going to look at something called a fatigue damage spectrum, and it's going to be based on rainflow fatigue. But in the meantime, let's just wrap up here. The vibration response spectrum, VRS, is a useful tool for comparing the effects of different PSDs on a single degree of freedom system, where the natural frequency and amplification factors are independent variables. In our case, when we did the VRS, we varied the natural frequency and held Q fixed, but a more proper use of this tool would be considering different Q values if Q is unknown. The VRS can also be used to determine whether a component which was previously tested to one Psd specification needs to be retested for a new specification. The VRS can also be used for deriving envelopes for measured PSDs from flight data or field data. And again, a preview of things to come, we're going to extend this concept to fatigue damage spectra in future webinars. So I hope you've enjoyed this webinar series, and if you have any questions, you're welcome to contact me. And I've got several emails that I answer to, and this one is as good as any. You can contact me at tom@vibrationdata.com. So I hope you can make use of these tools for your practical work problems. And thank you, and goodbye for now.